Ya Allah. Okay, I'm sorry, is it clear my voice? Okay, uh, good afternoon everybody. Uh, Let me introduce myself. I'm Solihon, and also already introduced by Isi Sensei. First, I would like to thank you very much for the time that given to me to give uh, something like maybe sharing about research and also collaboration between Universitas Gadjah Mada and Kanazawa University. And also I would like to thank for the committee and also for my teacher, Professor Mino Saito, that not only taught me about the research, but also we create the collaborations, academic collaboration and research collaboration after my graduations from Kanazawa University. The title of my presentation is First Principle Simulation of Defective Material. This is just a sample of our research, and in this time I also will share about the collaborations, research and academic collaboration between Gadjah Mada University and Kanazawa University. Now I'm Associate Professor at Physics Department, Universitas Gadjah Mada, and also because of this collaboration, I also collaborative professor at Kanazawa University. Okay, uh, I will share about two things. The first is research collaboration, which is related to density functional theory, uh, and about the academic collaboration that we create. First, density functional theory of our research. Actually, in the Department of Physics, it is not many researchers that research about the density functional theory. Right now, it's only me and also my colleague, uh, Dr. Muhammad Atibulil Absar, also uh, the student when we were a doctoral student in Kansas University. We were supervised by Professor Mino Saito, and for Dr. Muhammad Atibulil Absar, supervised by Professor Mino Saito and Professor uh, Ishi. And let me share our research. Uh, this is my research, for example, about the defective material from two-dimensional to three-dimensional, something like this is two-dimensional material like silicon or germanium, and then we drop some other atoms in here, and then we check or we analyze the difference in structural and also electronic properties. We also analyze the symmetry because actually I'm interested in the study of the stability of the geometry, for example. So we analyze the symmetry like Young-Taylor symmetry, or we know Young-Taylor symmetry. Uh, we analyze the breaking symmetry from the symmetry of the pure crystal, for example, silicon, uh, one of material in transistor that uh, Saito Sensei mentioned, germanium, for example, or diamond, and uh, how if we create a defect or we simulate a defect by removing one atom, like a vacancy, or introducing additional atom, for example. How about the symmetry? Does it will break, and what is the implication of the breaking symmetry? And then Dr. Atib now research about the uh, related to spintronics, also two-dimensional material like WS2 and others, decalcogenites and others. Uh, he analyzed the symmetry breaking, also spin orbit interactions. This is the application of the spintronic devices. And our collaborators in here is, of course, Professor Minasaito, Professor Isi, Dr. Yamaguchi, Professor Hersoy from UKM, Dr. Iman Santoso, Dr. Patricia Lubis. She is also a student of, like us, of Professor Mina Saito when she was in the doctoral program in Kanazawa University. Then Dr. Saswan Arman Wela, he is he was double degree program in Kanazawa in ITB. Also Nadia Amalia, they are both from Brin. Brin is the now is the new name for the research institution in Indonesia, something like RICAN in Japan. And now uh, uh, many institutions, small institution, and then combined become, we call it BRIN, like RICAN. Then for the research that we conducted from this is uh, germanium multi-vacancy, we check the stability of the geometry. In the silicon case, it was conducted by other researchers, which was published in the physical review, and then they compare the stability between the pairing models and uh, other model. So this is, for example, we treat three vacancies. Three vacancies. In the conventional model, if we create three vacancies, we just remove, for example, one atom, and one atom, so three atoms. And then based on the pairing model, so the symmetry will not change, but we saw that in here that the symmetry change to the lower symmetry. We call it breaking symmetry from higher symmetry to lower symmetry. This is a very interesting model, I think, and we published it in the Japanese Journal of Applied Physics. This publication is once after it was published once after I graduated, but I conducted this simulation when I was in Kanazawa University in 2015, and then we also simulate the NV, or this is nitrogen vacancy diamond. Nitrogen vacancy diamond. We check the symmetry, the stability, and so on, and then we simulate it using density functional theory. This is using GGA. We published it in Indonesian Journal of Chemistry. And then for the this is three-dimensional diffective crystal, and for two-dimensional is like hexagonal boron nitride. This we can see that this is in the initial form, this is pentagon, right? But this become octagon. This is the change during the relaxation, and then if we simulate accurately, if we simulate accurately, we will find the big breaking symmetry for this material. But if our simulation is not so accurate, maybe it will be trapped in the local minima, not global minima. Global minima means in the ground state of the system. If not accurate, for example, of the total force is not so small, so the energy may be not in the ground state, but still in the excited state, or we can say in the local minimum, not global. Another thing is about the two-dimensional material, also it is germanium. Germanium, this is hexagonal boron nitride, which is flat, not bulk. For the case of germanium, it is bulk or pucker. We also analyze the dangling counting model that I will share in the next slide. And this is not DFT, but using Trotter-Suzuki method for disorder graphene. We use some of million of particles in here using bracket crystal, and we saw that the result is similar with the DFT. Another thing is we just start the research about the drug delivery application using C60 or buckyball, and we analyze the interaction between this buckyball tolerance with the molecule. This is a sample of drug molecules, and if this is interact each other and then but not so strong than covalent, so maybe in the next analysis we can research more for the application of drug delivery. Another is the application of germanium for the methyl mercury. This is methyl mercury is heavy metal. Methyl mercury is toxic, and then how germanium become like a filter or sensor. And the new one is we also study and research about thermoelectric using using XTE, germanium, SM, tin, and PP, and then we simulate for mono and pi layer. And the next we will give the we also analyze the doping. We collaborate with Dr. Nidya and Dr. Arman from PRIL. This is also about the stability. Like I mentioned that I'm restricting in the stability case. This is we propose the model in here, like we using the formation and dissociation energy, and then we check, we shot the magic vacancy number. Magic vacancy number is the number vacancy system that which is very stable, and this is shown by this peak 6, 10, and 14, and so on. And we check also using the Dunkling bond counting model, and the result is occurring wells. And then this is the research of our colleagues, Dr. Adib. He focused on spintronic. There are many publications, and he is one of the lecturer in Gadjah Mada University that has many publication. This is using the two-dimensional material like WS2, WSE2, and so on, and then group 4, and then family GAXY, and other two-dimensional. This is some of his publication, and some of their publication is collaborate with me. And then maybe 5 minutes or 4 minutes, maybe I will share about the academic collaboration that was created, and we will improve and develop the collaboration between Ganasea University and also maybe with other university in Indonesia or other country. Right now we have double degree program for all master program in our faculty. Those are master in physics, master in chemistry, master in mathematics, and master in computer science and electronics. And of course, the exchange program between Ganasea and Universitas Gadjah Mada. And other thing is make scholarship that provided for UGM alumni, and we know that also ITB alumni to study master and doctoral program in Ganasea University. This is a good program. I think that we need to continue. This is, let me share about some picture that is in this picture. Professor Mine Saito and Professor Masato Kimura in 2000 in 2016 visited to Gajah Mada University, and they recruit of make scholarship for UGM alumni, and we initiate the degree program. So our program is start from this year. We uh, we meet with our dean, and then we visit after Professor Saito and Professor Kimura visiting us. We visit back to Kanazawa University with our dean. This is Dr. Bukit Marnor, dean in that time, but now uh, is changed. And this is vice dean of academic, and this is me in 2017. I'm sorry, I only have this picture. This is in front of I think the famous mosque and the only mosque in the Kanazawa city. And in the 2017, we also have met with President Kutsu Yamazaki, visited in our faculty. In here, we discuss many things about the possibility of collaboration, either research or academic collaboration. And then we visit again with many delegates, more than maybe about uh, 8 delegates maybe. And then uh, we meet again with the team of DDP, Prof. Saito, Prof. Isi, Prof. Nakawa, and other professor, and also we meet with President of Kanazawa again to continue the discussion. This is we meet in Kanazawa with Indonesian Student Association. Okay, and then this is the ISCS in 2017. Which was held in Kanazawa, and there are many delegates from UGM, UGM, and also ATP in here. So this is all, and again, thank you very much, and we open the collaboration and add the possible collaboration between UGM, ITP, and Kanazawa University. Thank you very much. Yes. Okay. Pardon? Oh, this is you mean this graph? Okay, this is from the value the energy of the dissociation energy. So the dissociation energy is energy that needed to dissociate. Uh, if the energy is small, uh, so the system is difficult to dissociate. So uh, the smallest energy is in this peak. I'm sorry, this is negative peaks. I mean, this peak is at the hexa vacancy, and this is peak in the octa vacancy, and also for 14 vacancies. This means that hexa vacancy is difficult to break become other vacancies. Uh, and also then this is we propose using this model, uh, and then we conclude the magic vacancy numbers. Magic vacancy numbers mean that number of vacancy which are stable in that system. In this case, the magic number are 6 and 10 and 14, and if you simulate many vacancies, so you can we can know this this number. So if we propose that the next magic vacancy number is uh, this is 4 and 4, so 18 using this, and we check using other uh, conventional model using the dangling bond counting model, but this model is using our energy, so we call it dangling bond counting model DFT. Using this, and the result is similar, even though the peak is maybe rather different, but the peak tends to the same number. For example, 6, 10, then 14, something like that. Okay. Okay, thank you, Dr. Manaf. It is the very interesting question, and also maybe rather difficult to explain. But this magic mean that not any numbers is of the vacancy are stable. So because the number of the vacancy uh, tends to the rule, for example, in this case is for n plus 2, for n plus 2, if n is 1, so we get 6, and then for n plus 2, if n is equal 2, so we get 6, and if n equal 3, we get 14. So there are two reasons. First, uh, because not any number are stable in the system of the system, and the second, these tables vacancies uh, create unique series. And the third reason uh, I adopt this magic word from the publication of Saito Sensei in the Japanese Journal of Applied Physics, maybe in 20, I forget. He or they used word magic numbers in graphene multivacancies. And because we conducted this using this is hexagonal boron nitride, and then we use the title magic vacancy number in hexagonal boron. And this is for the review, this is okay, and then I didn't change the title until this paper was published in the materials today communication. Thank you. Uh, thank you. And one thing that this needs more computational cost, because we need this very large supercell, right? And then many number of vacancy. This needs a long time, and we usually use 64 or 128 cores CPU core for calculation. It needs maybe about uh, 2 weeks until 2 weeks until 1 month everyday calculation. Thank you. You're welcome. Thank you.